Konnichiwa, Negi-san here again, and today we're looking at Run and Gun being played on a TV. Well, we are looking at Run and Gun being played on TV, but that's not the point of the video. The point of the video is this. Now, it's not the board, it's not the box. This, you see this PCB? Have you seen it before? On my, you might have seen one of my former videos about how you could use shift registers, and that was very complex and I was very tired. Now you see there's quite a few chips, there's a blinking LED if I do that, and then there's 555 there. We follow this cable all the way down, and we've got an NES controller at the end. And, quite literally, if we go into the test menu here, we have an actual working NES controller working and playing on a, an arcade board. Now ignore the colours because the pots haven't been set right, but you can see if I press A, it says A. If I press B, it says B. And if I do select, that's C, start, working, all good and dandy, no problems whatsoever. Now, this, you might think that's a pretty, it might be a really good, sorry, I'm trying to think. You might think that that must be a complex thing that it's doing, and it's really not. Now, as I said in my previous video, these controllers are essentially shift registers. They take the 8-button input that you see here and they convert it into a serial format which is doable with a shift register. So these are essentially just shift registers that get sent down into a cable, literally only having power, ground, clock, data and strobe or latch depending on your point of view. And this is going straight into this board, and these mesh of wires, you don't have to worry about it too much because most of those wires are actually coming from the jammer harness, and all this is doing the exact opposite of the controller and a couple of other things. Now the chip over there is doing the timing, and I'm not going to go into too much detail, just doing the timing. At the minute I think it's set for 128 times a second it pulses. Now that's pretty fast, but it's not fast enough, and I'll get onto that in a minute. Second chip is our timer that just basically allows us to time when to pulse the data, because obviously if you just kept clocking the data out it would eventually run out and it wouldn't have any more. So that little blinking LED is telling me how often that controller is getting its data latched. And then we've got the shift register. This is a 74595 shift register. This is a CMOS version of it, and all that basically does is take serial data in, convert it to parallel and send it out when you latch it. So literally it's just the exact opposite of the NES controller. The NES controller converts the parallel buttons into serial data, and this 595 converts the serial data into parallel buttons. And it literally, the outputs get straight connected to the jammer harness, and that's fine because when the controller is not pressed, all the inputs are high. Now that means they're getting 5V output TTL logic, and that's fine because pretty much all of the jammer games, the reason you only have to directly connect buttons is because they're all held up by internal pull-up resistors, and these things here, these resistor packs. And it means that these are always held in the state of being high, so feeding it the same voltage that is already there, so TTL 5V, it means that the button's depressed here. Now thankfully, because Nintendo are very nice, the design is very much like you would find in a cabinet, so that when you're not pressing anything it's high. When you're pressing it, however, you ground the button. So I'm grounding the B button, and although usually that would send 5V, it's now sending no voltage at all. Obviously this converts that data, and then it grounds it here, which means you're essentially just taking a wire from ground and putting it on that pin, which is exactly what a button does. So in essence, the entire circuit board there is converting this controller into a parallel format that the arcade board can then understand, and it's really good. The system's really good. The only problems are there's a tiny amount of input lag. Now you won't notice it because you're not here, but I'll tell you, there's like, I don't know, a good couple of milliseconds of pressing the button and then it actually doing something. It's not bad, you can still play a game nicely, but it's something you can be, if you're a fussy person, you'll definitely notice it. Pardon me. And yeah, so but that's a simple fix. That's literally just changing these resistors on this 555 and changing the cap, and then that's it, problem sorted. And that's why you do these breadboards first, because that way you know you go through this, check it all works, and then you make the PCB. Am I going to make a PCB? Eventually, just not anytime soon. Anyway, so yeah, and also another good thing about this is now I can use NES controllers. I can use SNES controllers. SNES controllers and NES controllers are almost identical. The only difference is that the SNES controller has 2 shift registers, meaning instead of having the 8 inputs you have normally on a controller, you can have 16. Now there are not 16 buttons on the SNES controller. However, the concept's still there. The only difference you have to do to read these is instead of latching the data every time you get the 8 bits of data out, you would instead you'd latch it every 16 times. So, and I mean, if you were to just cut an NES controller and solder on a SNES plug, it would work. And if you were to cut, do vice versa, it would work the same. They're exactly the same, and it doesn't matter that the NES controller doesn't have as many bits as the SNES is expecting, because it will only send out zeros and ones depending on what its button states are, and when it runs out of data it just starts sending ones again. So yeah, it's quite nice that you can do that. And I mean, if I wanted to read SNES controllers on this, say for like Street Fighter games, which I'm never going to get, all I'd have to do is put on a second shift register and make my timing circuit time every 16 times, because at the minute it's going latch data, so on and so forth until it gets to the last bit, and then the next pulse is latching again. So yeah, I mean, and like I say, we're just using a 555, a Johnson counter, and a 595 serial in parallel shift register. Yeah, this isn't the start, this isn't the end of this, because this is just a prototype. You always design the prototype and then you build the product you actually want. I have bigger ideas for this, and yeah, I will be making more videos. Oh, and if you're curious, this Xbox down here with this cable coming out, this is actually Psycho94's project. It's what he calls the J-Box, and essentially he's taken a dead Xbox, stripped it all of its parts because it was dead, like beyond repair. We tried it, it was gone. So we basically changed it so that it's now a jammer playing Xbox, which is great. And he designed, we kind of both designed it. It's his project and his idea, but we both designed it. And here we have the little control panel, which is really useful because it's got a test switch that works. Service credit, and then these are LEDs to say the 12 volt and 5 volt status. So at the minute, obviously the 12 volt and 5 volt are working. Doesn't do 3 volt or minus 5 volt because, to be honest with you, most boards, jammer boards don't need 3 volt because they're not designed to have that. And secondly, the majority of games don't actually need minus 5 volt. Games like Midway games do, but that's a different kettle of fish. Anyway, point of the matter is I've essentially managed to convert a NES controller into jammer, and I'm very happy about it. And it means that I can go ahead with one of my projects. Yeah, so one thing I will mention, when I said about pull-up resistors, if you don't quite know what I mean by that, it's when I talk about TTL, I'm talking about logic. So logic in electronics is like what state is something, and doing addition, subtractions, loads of stuff like that. I'm not going to bore you with the details. What I'm going to say is, what a pull-up resistor or pull-down resistor does is it makes an input into a certain state until you change it. So in the case of jammer games, they have a 10 kilo ohm resistor on the 5 volt line and the input. So essentially, when the game's asking what is the input at, it then goes it's on, because 5 volt means on. Now that's all good because you can set it into any state, so you can actually put it onto ground and say this is now ground, so this is off or 0. And yeah, the reason that, and I mean, you might, if you know your electronics, you know that you should never connect ground and 5 volt together. Now usually when you do that, the stuff shorts out and stuff goes bang, but that's what the pull-up resistor stops. It's when you, sorry about that for that jump cut. Yeah, so basically when you have input, well, as far as logic concerned, you should never connect 5V and ground together. That's just big no-no. Now, what the pull-up resistor does is it makes it so that the current going, it's basically got a load between 5V and ground, because when the electricity is going through, the electricity finds, generally, like most things in physics, try to find the path of least resistance. So it will go straight into the. So when you ground the signal, or turn it off, instead of the 5V going into the controller, or the ground and the 5V mixing together and going bang, basically the resistor is there to protect it and protect the device, and basically, like I say, it keeps it into a certain state, and it basically protects the board. That's essentially how it works. It's a very simple system, and I've gone on for long enough for a very simple announcement, really. But yeah, I hope you've enjoyed watching this and find something useful about this. If you have any questions about this, just give me a bell. And yeah, I will be upgrading this in future. Don't know if I'll be putting a video up on it, but we'll see. Thank you.